All right, so the topic for this video is going to be similar right triangles. And our essential question we're going to be trying to answer here is when are similar right triangles formed and how are problems solved with them? So these past few videos, we've really been looking at similarity and proportions and kind of following along with what our guy Euclid did back in the day, the father of geometry. And so what this says is Euclid continued to examine similarity and proportions. One such situation involves similar right triangles. So what are these things? Similar right triangles. If the altitude is drawn to the hypotenuse of a right triangle, well, let's first kind of illustrate that. So if we've got this big right triangle, and then we draw the altitude, remember the altitude is the line segment that is perpendicular to the opposite side. So if we draw in that altitude towards the hypotenuse of the right triangle, then the two smaller right triangles that are formed are going to be similar to the original triangle and to each other. So what we're talking about here, we've got the big right triangle. We've got the little right triangles. So all three of those triangles, yellow, green, blue, all of them are similar to each other. Okay? Those are going to be our similar right triangles. So example one, we're just going to try to complete the similarity statement here, just try to line some things up. So triangle ABC is similar to something, similar to something. Okay, so let's follow ABC real fast. Down the short leg, down the long leg, back along the hypotenuse. So let's try to line that up with our small right triangle. So if we did ABC, we need to do ADB for the little one. And then for the last one, the short leg is BD, so BDC. So those are going to be our three similar right triangles. Notice all of them have the right angle in the middle, right? A, B, C. B is the right angle of the big triangle. A, D, B. D is the right angle of the green one. And B, D, C. D is the right angle of the blue one. All right. Now, some cool things happen when we've got some similar right triangles. Before we start taking a look at those, first, let's talk about this term geometric mean. The geometric mean of two numbers is defined as the square root of the product of the two numbers. So let's say we've got two numbers. Let's say we've got, let's do, what do we want to do here? 4 and 9. If we want to find the geometric mean of 4 and 9, first, we multiply them together to find the product. And then we take the square root of that. So the geometric mean of 4 and 9 would be 6. The normal mean, the algebraic mean, you add them and then divide by 2. The geometric mean, you multiply and then square root. Okay. Now, the reason that we're bringing that up is that we've got some things going on inside these similar right triangles involving geometric means. So the geometric mean altitude theorem says, if an altitude is drawn to the hypotenuse of a right triangle, then the length of the altitude is the geometric mean of the two pieces of the hypotenuse. Okay. Sounds complicated. Let's draw our similar right triangles again. And so what we're saying is that the altitude there is the geometric mean of the two pieces of the hypotenuse. If I give some letters here, we can write it out. So AD over DB is equal to DB over DC. That's the way that I just highlighted it there. I started with that first piece of the hypotenuse, AD. AD over DB, the altitude, is equal to DB over DC, the altitude over the other piece of the hypotenuse. Okay? Now, it still seems weird, I know. Check this out. Solve for x. All right? So x is on the altitude. If you're using the altitude, we're going to use this altitude theorem. So what we do that same highlighting pattern that we just did, and you'll see it all kind of come together. All right, so I started by highlighting the piece of the hypotenuse, the 9, right? So it was 9 over x. Then I went back down x, and then I went down to 4. Okay, so 9 over x equals x over 4. Now, what I did was I set up a proportion, right? Well, when we cross multiply, x times x is x squared. 9 times 4 is 36. And if I want to solve for x, what do I need to do? I need to take the square root of both sides, right? Get rid of that x squared. The square root of x squared is x. The square root of 36 is 6. So take a look at what I just did. I multiplied 9 and 4 together, and then I took the square root of it. And if you multiply two numbers together, then take the square root, you are finding the geometric mean, right? So the altitude is the geometric mean of the two pieces of the hypotenuse. So that's it kind of all coming together. Now the way that you set up those problems is by doing that little highlighting pattern that I just did. But that's how it relates back to the geometric mean. That's how it relates to proportions, right? We solved that by setting up a proportion. And we can set up that proportion because those triangles are similar. Okay? So it's all kind of coming together here. All right, let's take a look at the inside. We can try a few more here. So solve for x here. Okay, so once again, there's something written on the altitude here. So let's do our highlighting pattern. 8 over 4 equals 4 over x. 8 over 4 equals 4 over x. We cross multiply. 8 times x is 8x, 4 times 4 is 16. We divide by 8 this time, and we get 2. Okay, now if x is 2, let's see if 4 really is the geometric mean. Well, we take the two pieces, right? 8 times 2, we get 16. The square root of 16 is, in fact, 4. So, yeah, 4 is the geometric mean of 8 and 2. The altitude is the geometric mean of the two pieces of the hypotenuse. Give ourselves a check because we checked our work. Okay, this one. Let's see what we're doing here. Down one of the pieces of the hypotenuse, down the altitude again, down the other piece. So that was 12 over x equals x over 4. When we cross multiply this time, we do get a x squared, and 12 times 4 is 48. Now, unfortunately, on this one, when we take the square root, 48 is not a perfect square, so we don't get a good number. So now we got to remember how to simplify some radicals. When I do that, I like to break it down into different factors. And I try to find some factors that are perfect squares, because I know I'm trying to take the square root. Perfect squares are good for square roots. So one thing I could do is I could do 16 times 3, because 16 is a perfect square, right? I get a pair of 4s there. So remember, if you get a perfect square, you get to bring that to the outside, and then you leave the thing that doesn't have that isn't a perfect square on the inside. So that would be 4 square root 3. And there we go, 4 root 3. Cool. All right. What do we have next? Okay, so another geometric mean thing, but this time we're not dealing with altitude, we're dealing with the leg. So this says that the altitude is drawn to the hypotenuse of a right triangle. Then the length of each leg is the geometric mean of the hypotenuse and the piece of the hypotenuse adjacent to the leg. Okay, so this one, same kind of drawing here. But this time we are not dealing with the altitude. We're dealing with one of the legs of the right triangle. So this is going to look like this. We're going to go the piece, down the leg, back down the leg, and then down the whole hypotenuse. So if I label this, this would be dA over AB is equal to AB over AC. Okay, you start with the piece of the hypotenuse, then go down the leg, wrap back around the leg, and then down the whole hypotenuse. That's how you're going to set up that proportion. And see how these problems, like if I look at example 5 here, notice there's nothing written on the altitude, right? So we're not going to be doing the previous theorem. This time we got to deal with the leg theorem. So 5 over x equals x over this whole thing. So that was 5 over x equals x over the whole thing there. 5 and 15 would be 20. So cross multiply, x times x is x squared. 5 times 20 is 100. Take the square root and we get 10. Now, we can check that by seeing, is 10 actually the geometric mean of 5 and 20? 5 times 20 is 100. Square root of 100 is 10. Okay, so we did that right. So the leg is the geometric mean of the piece of the hypotenuse and the hypotenuse. Let's try that one more time. This one's kind of tricky. I see that x is on the leg BC, so I start with the piece of the hypotenuse that's close to that leg, go down the leg, and then wrap back around. So that was 2 over x equals x over the whole thing here is 10. So when we cross multiply here, x times x is x squared. 2 times 10 is 20. Take the square root of that. 20 is not a perfect square, so we are going to have to simplify it. We could do 4 and 5 because 4 is a pair of 2's. So remember, the 2 comes out, the 5 stays in. So simplified, that would be 2 square root 5. Okay, we're cruising right along. So now let's try to stick all this stuff together. So this one says solve for x, y, and z. We've got the similar right triangles. We've got a lot of variables flying around. Let's start with x, because x is on the altitude, so we can do the altitude theorem. Remember, the altitude theorem's highlighting pattern looked like this. We did 12 over x equals x over 3. We cross multiply, x times x is x squared. 3 times 12 is 36. Square root of both sides. 36 is a perfect square, so we get that x is 6. Now I'll kind of put that in some green so I know that was how I solved for that one. Now, one of these legs here, let's try to find y. So y is on one of the legs, so I need to do the leg theorem. So I start with the piece of the hypotenuse that's close to that. I go down the leg, and then I loop back around. So for that, that would be 3 over y equals y over this whole thing here is 15. So cross multiply, y times y is y squared, 3 times 15 is 45. Square root that. 45 is not a perfect square, so I could do 9 and 5. I like that because 9 gives me a pair of 3's. So I get to bring a 3 outside and I leave the 5 on the inside. Okay, now we still need to find z. Now z is another leg. So I need to do the leg theorem again, but this time I'm going the long way. So I need to start with the big piece of the hypotenuse, then go down the leg, and then loop back around. So that time I started with 12, went down z, back down z, and then down the 15. Z times z is z squared. 12 times 15 is 180. Yes. 180 is not a perfect square, but I could do 36 and 5. And 36 gives me a pair of 6's. So I can say that z is equal to 6 square root 5. And there we go. I had to do all 3 there with 2 of the leg theorems and 1 of the altitude theorems. All right, let's check the last one. We got one more like that. Okay, I like to start with the altitude. So let's go this way. And do 6 over x equals x over 18. When we cross multiply, we are going to get x squared equals 6 times 18. 6 times 18 is going to be 108. And square root that. 108 divided, I could do 36 and 3. 36 gives me some 6's. So I'm going to say that x is 6 square root 3. Okay, now let's grab one of the legs. I'm going to go for y next. Start with the piece of the hypotenuse near y. Go down y and then loop back around. So that'd be 6 over y equals y over the whole thing, the whole hypotenuse, which is 24. It's going to give me y squared is equal to 6 times 24, which is 144. Take the square root of that, and that's a perfect square. Get y is equal to 12. And then lastly, we need to find z. So for z, I'm going to start with the 18, go down z, and then back around. So that's going to be z over 18 No, I'm sorry, 18 over z. 18 over z is equal to z over 24. That's z squared is equal to 18 times 24 is 432. Well, we're going to take the square root of that. And what can we do here? I think we can divide it by 36. No, maybe 64 even. No, let's divide it by 36. I think we can do better, but let's find out. So divided by 36 is 12. Okay, so that's going to give me a pair of sixes. But this 12 also can go to 4 and 3, and that 4 gives me a pair of 2s. So actually I can bring a 6 and a 2 to the outside, and that 3 stays on the inside. And that 6 and the 2 on the outside multiply together to give me a 12. So I guess that means 432. I could have broken it down into 144 and 3, and that 144 would have given me the pair of 12s right away. But that's okay. Live and learn. And there you have it. We got z, we got x, we got y, all sorts of geometric mean theorems there. Okay, so your time to shine, trying those highlighting patterns and setting up those proportions. You've got two basic ones to try. You've got an altitude and you've got a leg, and then you got one big one like we were just doing. So give those a shot and then come back when you're ready to check to see how you did. All right, so example 1, we had the altitude here. I would have done 8 over x equals x over 24. X squared is equal to 8 times 24 is 192. If we square root 192, that could be divided by 64. Yeah. 64 and 3. 64 gives me some 8s. So I'm going to get 8 square root 3. For our next one, we got a leg. I'm going to go 7 over x equals x over the whole thing, which is 21. So cross multiply, we get x squared is equal to 21 times 7 is 147. Square root that. Pretty sure we can get a 49 out of that. Yep, 49 and 3. 49 gives me those nice pairs of 7s. So I'm going to say 7 square root 3. Then our last one, the big one. So let's grab x first. 30 over x equals x over 10. It's going to give me x squared is equal to 300. 300, I like 103, because 100 gives me the nice pair of 10s. So x will be 10 square root 3. What else do we have? Well, for y, I can do 10 over y equals y over 40. 10 over y equals y over 40. Y squared is equal to 400. Square root that, I can do 100. No, that's just a perfect square. Ooh, that's just 20. Nice. Okay, and then lastly, we can get z by doing 30 over z equals z over 40. Cross multiplying there, we get z squared is equal to 1200. Let me take the square root of that. I think that can be 403. That 400, like we just saw, gives me a nice pair of 20s. So I will say that z is equal to 20 square root 3. And there we go. 20 square root 3. Cool. All right, so hopefully y'all did pretty good there, and that's going to wrap up our video.